Dear learners, myself Ashwini Patil, Assistant Professor from Department of Pharmaceutical Chemistry, Govindrao Nikam College of Pharmacy, Savardi. Today in this video, I am going to explain benzene and derivatives. After listening to this video, learners will be able to understand the structure of benzene, explain the reason for stability of benzene, and draw the orbital picture of benzene. Benzene, on which the study of aromatics began, was discovered in 1825. However, its structure wasn't known till 1866. It is extremely unsaturated structure with only one atom for every atom and was difficult to work out. Several scientists have tried to explain the structure of benzene, but due to insufficient proof, no explicit structure was accepted. In 1866, scientist Kekule has proposed acceptable structure of benzene, which is having alternate single and double bonds in a ring of 6 carbon atoms, each having one hydrogen attached. As you can see in the slide, this is Kekule formula for benzene, having molecular formula C6H6. Kekule structure of benzene has satisfactorily explained various substitution products shown by benzene. Let us move towards several analytical and chemical or synthetic evidences given to the structure of benzene. Coming to analytical evidences, if the benzene is a simple cyclic alkene, that is cyclohex 1,3,5-triene, then it was expected to have alternate shorter and longer bonds. But in reality, the bond length of all carbon-carbon bonds in benzene was found to be same, having value 1.395 angstrom. Second analytical evidence can be seen by enthalpy change associated with the hydrogenation of benzene. It was supposed that the enthalpy change for hydrogenation of benzene was 3 times that of cyclohexane, because cyclohexane has a single double bond, whereas benzene has 3 double bonds. But the reported values haven't proved this statement. The reported value for enthalpy change of hydrogenation of benzene, instead, as expected, that is 360 kilojoule per mole, was found to be minus 208 kilojoule per mole. Third analytical evidence, alternate, as benzene is having alternate single and double bond, it was expected to have a bond length which is intermediate between carbon-carbon single and carbon-carbon double bond. But as we have discussed, all the 6 carbon-carbon bonds in the benzene structure have same bond length, and the value is 1.395 angstrom. Thus, it can be said that benzene is a regular hexagon with identical bond angles 120 with molecular formula C6H6. All the 6 carbon-carbon bonds have same bond length, that is 1.395 angstrom. Moving towards synthetic or chemical evidence, we can see the nature of bonds is not truly alkene type, as evidenced by the fact that benzene is resistant to most of the reactions shown by alkenes. For example, alkene gives addition product when treated with bromine water, which shows decolorization, whereas benzene do not undergo addition reaction. Benzene, when added to bromine water, does not show decolorization. This proves that the nature of bonds in benzene is not truly alkene type. So thus, the structure of benzene can be shown as alternate double bonds having a character which is neither of single nor of double bond. But benzene is an average of the two structures. You can see it in this slide. Here, I request all of you learners to take a pause and think on this question and try to answer this question. The question is, in actual structure of benzene, the bonds which are formally double do not behave chemically like double bonds, but as a much stable and less reactive functionality. What might be the reason? I request all of you to pause the video and note down the answer in your notebooks. Yes, I hope you have written the answer. Now, in order to understand the stability associated with the benzene structure, let us have a look on the two structures. It can be noted from these two structures that the two structures have same number and kind of bonds and therefore must be equal in energy. The difference between two structures is that the double bond are present in first structure between carbon number 1 and 2, 3 and 4 and 5 and 6, whereas the position of double bond in structure 2 is between carbon number 2 and 3, 4 and 5 and 1 and 6. In the actual structure of benzene, all 6 bonds are equivalent and are intermediate between double and single bonds, as evidenced by the molecular orbital calculations, which indicate a bond order of 1.67. Yes, in actual structure of benzene, the bonds which are formally double do not really behave chemically like double bonds, but as a much more stable and less reactive functionality. This is because all the 6 pi bonds in benzene are delocalized. All the 6 pi electrons in the benzene are delocalized over all 6 atoms and are not uniquely shared by a given pair of 2 atoms. This delocalization of pi electrons is nothing but resonance. That is the reason for stability of benzene. And benzene structure actually is a resonance hybrid of these two resonance forms, also called as canonical structures. In order to see this, let us have a look on the orbital picture of benzene. Now, as in Kekulé structure, each carbon is said to be trigonal. That is, it is a planar structure with sp2 hybridized carbons. As all the 6 carbons are sp2 hybridized, each carbon is attached to 3 different atoms, 2 other carbons and a hydrogen. Whereas the 2p orbital, which is present on each of the 6 carbon atoms, lies above and below the plane. When these 2p orbitals of all of the 6 carbon atoms are mixed, it results into the formation of 6 pi bonding molecular orbitals. As they overlap in sidewise fashion, the pi electron cloud in benzene lies above and below the plane. It can be shown in the form of violet color in the slide. You can see the pi electron density looks like a donut shape, meaning the pi cloud lies above and below the plane. These pi electrons, they keep continuously on changing their positions. This is all about orbital picture of benzene. To summarize, in this video we have seen the Kekulé structure of benzene, the most acceptable form, then analytical and chemical evidences to the benzene structure, resonance in the benzene, that is the reason for stability of benzene structure, and orbital picture of benzene. Dear learners, thank you very much for your patient listening. Stay home, stay safe and happy learning. Thank you.